Welcome back, everybody. I hope you can hear me well. Is the sound okay everywhere? Okay, so the topic today, as you can see also from the Jupyter notebook, is to now move into Kepler's laws and the gravitational force. So that means that we are going to derive elliptical orbits, and we are going to look at the consequences for the type of motion which we have for this type of system. And the harmonic oscillator, which we went through on Monday, is something which you will encounter again in the homework for this week. So if you go through the slides, the Jupyter notebook, which you're seeing here, you will find many hints for solving the exercises this week. And in particular, when you have to show that you get an elliptical type of orbit, there are some mathematical manipulations, which it's actually easy to get lost in the manipulations. And you will see that today when we're going to derive elliptical orbit for the gravitational force. There's another thing. I think this topic today is actually one of these topics which I really like the most. And it's full of small hidden gems. And my job today is actually to show you where these gems are, because they often give very nice small insights about a physical system. And the two-body problem, like you're going to see solved today, is something which was solved, I think the way we are going to do it today, 150 years ago. Newton actually solved this in the 17th century by using geometric arguments. And this is a topic which has been studied for 500 years. So it dates back to Kepler, Galileo, and so on. And there is I'd say 5 centuries of physics which are baked in to the solution of the gravitational problem. There's another problem which is also very interesting. That's a free body problem. So when we come to the second midterm, an intermediate step towards the full solar system is to look at the problem of free objects. It could be the moon, the sun, and the earth, which is the classical one, which Newton actually studied. But you could also look at the problem, and this is the one we look at in the midterm, of Jupiter, the sun, and the earth. This is also a problem which can be solved analytically. And it was solved analytically, I think, in 1912. So you can think of, you had hundreds of years of people trying to solve these equations analytically. So there is an impressive body of analytical solutions. When you do this numerically, it may be a little bit disappointing if you think of 400, 500 years. And numerically, it's just a few lines of codes. And then you can visualize it immediately. So in a certain sense, we are a little bit more fortunate. But I hope when I guide you through these tricks, because some of these tricks are actually pretty useful to have seen when you move on to other physics courses. However, before we move on, let me just bring back on the whiteboard the harmonic oscillator case, which we looked at last Monday. So let me just bring this up here. And oops, where did that disappear? So on Monday, we looked at this so-called effective potential. So let me redraw it here. And what we had is effective potential. We made the translation to, or the transformation to polar coordinates. So the potential depends only on R. And you can plot the energy of the system. And in our case now with the gravitational force, the potential, the effective potential, is going to look more like this. So we're going to have a V of R, which now moves over to a V effective, where we have incorporated a term from the kinetic energy, which depends only on the radius. And in our case, this V effective is equal to minus gamma, which is a constant, divided by R. And then we have this term, which is proportional with the angular momentum, divided by 2, the reduced mass, and then we have R squared. So this is the effective potential. And with the harmonic oscillator, we got a potential which has infinitely large walls when you go to R, to large values of R. So that means that for the harmonic oscillator, we will only have two types of motion. One, which was the circular motion. And for the circular motion, what we had was that we found the minimum here. And this minimum was given by the derivative of this effective potential of R min equal to 0. And that led to the total force being equal to 0 in the radial direction. And what we found then was that since this is actually the force being 0, so this is the force at R min, and we should write this as an effective force, this is given by the reduced mass and the second derivative with respect to time of R. Now, if you look at this term here, and you add to this one the expression for the kinetic energy, which we derived as well in polar coordinates. So there are two equations. So if you look at this equation here, this one, so this simply means that it's equal to 0 because the derivative of the effective potential with respect to R is gives us the force. And at this minimum, the derivative of the potential is 0. Then we have the kinetic energy, in this case, which is given by 1/2 times mu, and then I have R dot plus R squared multiplied with the angular velocity. And we had that the angular velocity of dt, which is something we write as phi dot, was given by L divided by mu times R squared. So that's the expression for the angular velocity. Now comes the question to you. So this is hidden gem number 1. Which kind of consequence does this have for the kinetic energy when you are at the minimum? So if you look at these equations now, these are the 3 equations which you need to think of. So we have one thing, the acceleration is 0, okay? That means that the radial velocity, if the acceleration is 0, that's the derivative of the radial velocity, right? So what value does the radial velocity take? So which value does the radial velocity take? So what we have is a acceleration, the radial acceleration, which is 0, at this minimum point. So what does that mean for this term here? It's a constant, okay? So here, at this point, we are looking at the kinetic energy calculated here. So that means that R squared is R min squared. Would you agree on that? And that's a constant, right? You are at the minimum. You place yourself at the minimum. You still have kinetic and potential energy. So the potential energy is not 0. It does not need to be. And the kinetic energy is not 0. Okay? So if you now look at these quantities which you have here. So phi, the angular velocity, which you see here, that's also constant, right? Because if I put in these equations now, if we put in R min, which is just a constant, so if I put in R equal to R min, we can rewrite this as, let's call this a constant 1, right? And then clearly R squared is just equal to R min squared, because we are placing ourselves at that position. So what does this mean for the kinetic energy as a function of time. So this is hidden gem number 1. It is conserved. The kinetic energy by itself is conserved. Now, if we now look at the next thing, so this is important actually. So if we have circular motion, if you're now testing energy conservation, that means that kinetic energy with circular motion is conserved as a function of time. It's conserved as function of time. Now, if I then go back to the potential energy, so my potential energy, in this specific case, since I have the harmonic oscillator, that was given by 1/2 this constant k, and then I have x squared. We were looking at the harmonic oscillator in 2 dimensions, and I have 1/2 of k r squared, and I obviously calculate this at r min. So this is actually given by 1/2 of k of r squared min. So gem number 2 should now be obvious, right? So what happens to the potential energy as a function of time? It's also conserved. So because r min is a constant now, and k is a constant, so this is just a conserved quantity. So this is the only case with this type of potentials where kinetic energy and potential energy are conserved by themselves. When we're going to go to elliptical orbits, what you're going to see then is that the potential energy will oscillate with time, and we will see that from the equations now. The kinetic energy will oscillate with time because x and y squared, when you add them, is going to change with time. But when we add kinetic energy and potential energy, then the total energy will be conserved. So circular motion is one of these exceptional cases where kinetic energy is conserved by itself and potential energy is conserved. And this is not limited to the harmonic oscillator. So when you take the gravitational potential, the kinetic energy is going to be the same. That doesn't change. But the potential energy, when we place ourselves at this minimum, so if we replace the harmonic oscillator with a gravitational force, so we have a V, which is minus gamma divided by R. And this is the same as minus gamma divided by x squared in 2 dimensions, or y squared. And if we plug in V of R min, that's simply going to be minus gamma divided by R min, and that's also constant. So if we have a effective potential like the one we are looking at now, so remember now that we have plotted everything as a function of the radius r. We could have plotted everything as a function of x and y, but then we would not have been able to see these things immediately. So a change of variables from Cartesian coordinates to polar coordinates allows you to see things in a different way. Any questions so far? So these are the kind of small observations which we can make on the way here. But now we are going to find the solution to this gravitational problem. So now I should just say, fasten your seatbelts, lean back, and let's slowly go through this. So now comes a lot of kind of mathematics, but it's actually the reward is actually pretty nice because we get equations which we can interpret very nicely here. So let me now bring back the gravitational force and let's look at the solution. So the task now is to go back to this equation which we have, the equation of motion, where we have the force, which is going to be gamma divided by r squared, plus this gravitation, this angular momentum term, which goes like mu multiplied with r squared, r cubed, sorry. So this is this centrifugal barrier. And we started with a potential now, which is V of R. And this is this effective potential. And this is minus gamma divided by R plus L squared divided by 2 of mu of R cubed, R squared. So in our case now, when we plot the potential, it's going to look like this. And this type of motion is going to be the same as we had for the harmonic oscillator. So we're going to get a circular motion, except that our min will be different by obvious reasons, because you have a different potential. But the kind of arguments to find our min is going to be exactly the same as we did for the harmonic oscillator. Now, what we are more interested in now is to find a different R min, which corresponds to this energy. So we are going to have an energy which is now less than 0. This energy which you see here, this energy prime, is also less than 0. And later we are going to look at what happens when the energy is 0, which means that when you make a plot here of the total energy, which is this one, we can look at situations here where the energy is 0, or we could look at situation here where the energy is larger than 0. And these 4 cases are going to give us 4 types of motion. And we can derive all these types of motion from the analytical solution to the problem. So let's try to find this analytical solution here. We have an additional equation which we need to use, which is d phi dt, which is phi prime, and this is L divided by mu over R squared. And mu is the reduced mass. So trick number 1, this is the first trick, and you will often see this kind of trick in the solution of this type of equation. And in this case, we are going to replace a R, define R equal to 1 over a variable u. And what we want now, and you will find this convenient because it's going to give us a simple equation to solve. So don't be intimidated by all these kind of details, because people have been playing around with these tricks for hundreds of years. So what you're seeing now is actually condensed knowledge and trial and error by many, many, many people. So you would often try tricks like this and see if you can simplify the equations. When you do this numerically, as I said, it's a little bit embarrassing because it's just a few lines of code. So the numerical approach is actually much, much simpler. So so what we want now is to have this R, the radius, as a function of phi. And there's a reason for that, because you see we have an equation here where we have phi as a function of time. And we have also phi, this derivative here, the angular velocity, which depends on R. So what we want to do now is to rewrite the equation. So instead of time, we are going to have an equation where we get R as a function of phi. And when we have R as a function of phi, we know how to solve the equation for phi, because that's a simple first order differential equation, which is this equation here, which is actually a pretty simple one in terms of phi. So the first trick now deals with that. And to do that, we need some, so we want actually R of t, and we want that expressed in terms of R of phi, where phi depends on time. So what we're doing now is simply to calculate dr d phi. We need that as an intermediate. So what you're going to see now is just a simple application of simple and simple. It's just an application of the chain rule for derivatives. So we would then have this one as a du d phi. So what I've done here is simply to take R being given by 1 over u and just plug that in. Does that make sense? So the next trick is actually to rewrite the time derivative in terms of a derivative with respect to the angle phi. So rewrite d dt in terms of d phi. And this is again just the chain rule, which I guess you are pretty familiar with. And we will then rewrite d dt, which is then d phi dt. And then we have d phi, which we rewrite like this. And we have that expression. We know that this is actually given by the angular momentum divided by reduced mass and multiplied with the radius squared. So we can actually rewrite this quantity in terms of L divided by mu over r squared of d phi. So that's the first rewrite. Then what we need now is obviously d dt, and we are going to, and we can rewrite that in terms of this quantity u. So we have L divided by mu, and then we defined r to be 1 over mu. So we have u squared and d phi. Then we know that the radial velocity, so this is the next step, is actually d of r dt. This is what we wrote as r dot. And if we now use that one, we can rewrite that in terms of L of this u squared of mu, and then we have d phi. So we are using this equation which you have here, this one, and replace d dt with that. And then we need to plug in 1 over u for r. Okay? Let me know if there are some transitions here which are not too easy. So if I now rewrite it and I take u, this simplifies to minus. So I take the derivative of this u with respect to phi, and I can rewrite that one in terms of minus L divided by mu, and I have the derivative of 1 over u, which gives me plus, and or rather minus 1 over u squared, and I have u squared in front of the equation, so this simplifies d phi, and then as a derivative with respect to u, like that. Let me know if something is unclear. So what we are doing now is, with these two tricks, we are simply doing a transformation of the equations. And what happens then is that we're actually going to have an equation which can be solved analytically in very simple ways. And you're going to recognize the equation immediately and see that the solution is going to be given by cosines and sines. And that's the nice thing here. So what we want at the end, we want actually d dt of dr dt. So this is the final step which we want. And we want this written out in terms of this quantity u and the angle phi. So this is nothing but our r dot, which appears in the equation for the acceleration. And this means that what we have now, when we plug things in, this is a d dt, and then I have minus L, and L is a constant, mu is a constant, so nothing happens there. And then I have a du of d phi, like that. And if I now take the derivatives and use the equations which I put up here, du d phi, we have the equation from above here, and then we can reuse that one, and then we plug that in. What we are going to get then is that r dot is going to be given by, since we now have the time derivative, and we already did this dt du d phi, we did it here. So we have this term which you see here. So if we plug that one back again, and do the algebra now, we are going to get minus L of u squared divided by mu squared of d of u of d phi second derivative. So I'm simply plugging in the expression which we had above for du d phi. And this is the same as the force which we are dealing with, divided by the reduced mass, plus L squared divided by mu over r cubed. And now we plug in the expression for the force. And we know that the force is actually given by, if we now remind ourselves, so F of r is given by minus gamma divided by r squared, which is the same as minus gamma times u squared. So if I do the algebra now, what we are going to get when I plug in u instead of r, we get the following expression. We get d u d phi. So this term here, I'm simply now multiplying away these parameters, so u squared, mu squared, and L squared. And then I put in the equation here. In here, I plug in the force in terms of u. So that gives me the following equation now. I get plus a parameter gamma, and then I have mu divided by L squared, and minus u here. So what I did was simply now to divide by L squared. And remember now that this term, which you see here, this term, that gives me, if we now rewrite this one, this is L squared divided by mu, and then it has u cubed. This term here is now simply minus gamma divided by mu and multiplied with u squared. So what I'm doing now is simply to divide by u squared everywhere. I divide by minus L squared and mu squared. And when I do that, I end up with a final expression, which is the one you can frame in and put at your bedpost and look at it before you go to bed every day. Now, if you now, let us assume now, just for simplicity, this is just assume that gamma is equal to 0, okay? So then we have a differential equation, du of d phi, the angle, which is equal to minus u. So what's the solution to that problem? Again, if you think back to harmonic oscillations and replace u with x. So this is a famous differential equation. When you see that differential equation, you should not even think. This has as a solution two famous functions. If I rewrite this in another disguise, so let me see if I can convince you. So if you look at this equation as dx dt is equal to a constant omega squared times x of t, and you replace t with the angle phi and x with u. So you were solving this in this homework, right? So which functions can we use for the solution here? Sine and cosine. So when you see this differential equation in whatever kind of disguise, you don't need to think. This is a cosine and sine. So what we have done by these two tricks and using the expression for the angular momentum, we have actually rewritten a differential equation which seemed not possible to solve in terms of something which can be solved. So you can now think of hundreds and hundreds of scientists throughout several centuries trying with different types of solutions, manipulating the equations. So it's not like when I saw this the first time, I was a little bit intimidated and asked myself, would I have been able to cook up this? Probably not. But then you have to think that this is actually a result of many, many people looking at the same problem. And then trying different tricks. So often when you solve differential equations, you try tricks like these. And sometimes you're lucky and sometimes you're not. So this is one of these cases where you can actually rewrite a differential equation in terms of a constant. So the term which you see here, the first one, is just a constant. So this is a constant plus an unknown quantity u. So what you could do now, when you want to solve this equation, so let's set up the solution here and do the final manipulations. So if I just take this equation here, this has a famous solution, which says that u of phi is equal to a times a cosine of phi plus a constant b, which is defined by the initial conditions of sine of phi. So that's the solution. Now, a standard trick, when you now have a constant like that one, so you can actually rewrite this one, and we can rewrite this in terms of a constant c, and this is something which goes back to our chapter on harmonic oscillations. We can rewrite this cosine and sine in terms of a cosine, and where we have a constant delta, which is defined in terms of a cosine and sine. So that means that r of phi, which is actually 1 divided by u of phi, is then equal to this 1 over c, a constant of cosine of phi minus delta. But then we have an additional term here. So what we're going to do now is to look at the constant term, which is this term here. Now, since this is a constant, we can guess on a solution which contains a new constant plus this solution, which we have already now. So what we would do then, in order to find the solution, is to assume that there is a new function, w of phi, which is equal to w to u of phi, u of phi minus the constant we have, which is gamma times mu divided by L squared. So this is the function which we guess now. And if I take the derivative of this function w in terms of phi, this is nothing but minus this w function. Because the quantity which we have after is just a constant. So that means that I can actually rewrite my solution here in terms of a new cosine function. So I could write this as a d, and now I'm going to be a little bit sloppy with notations here. I'm going to use the same delta here. And that means that so this is w, is not u, but now comes u. So I hope you can distinguish my different letters here. So that means that u is going to be given by mu times gamma divided by L squared plus a constant d times cosine of phi minus delta. We can always scale these angles so that this constant delta is equal to 0. So that means that I get u of phi, the solution, which is given by this constant, gamma, divided by L squared, plus a constant d of cosine of phi. Next, I bring these two together, and I'm going to rewrite this in terms of mu times gamma divided by L squared of 1 plus a constant epsilon of cosine phi. This epsilon has a name in astronomy, and it's actually called the eccentricity. It's not a very eccentric thing, but it's called the eccentricity, and you will see why a little bit later. So this epsilon is now defined simply as d, which is a constant defined by the initial conditions, divided by gamma times mu. So next, what I do now is to define a new constant. So this is just playing around and want to rewrite the equations. So I define a constant, which is now given by L divided by mu times gamma. And then I know that u of phi is equal to 1 over r of phi. So I can rewrite everything. So I can rewrite r of phi, that's what I wanted, as this constant c, which contains now the angular momentum, the gravitational constant, the masses of the object, if we're doing gravitational forces, and the reduced mass, and 1 plus epsilon of cosine of phi. So this is a solution, actually. So this coming Friday, when you go out and visit friends, you can actually present this solution to them. I have a suspicion, I probably said that, suspicion why people don't invite me to parties anymore. Anyway, this is actually a beautiful result, because now, if you look at this constant epsilon, if you put that one to 0, okay, which means you have 0 angular momentum, for instance. What kind of motion do you get then? If I put epsilon to 0, what is the radius as a function of phi then? C is a constant, keep that in mind, right? But I put epsilon to 0. So what's the radius then? Constant. It's a constant. What kind of motion do you get if the radius is a constant? Circle. So you can actually infer immediately by looking at the equation, if epsilon is 0, this is a circle because r is a constant. Okay, so this is pretty neat. So by just looking at the equation and looking at this quantity epsilon, you can then infer that the solution has to give us circular motion. So epsilon equal to 0, that means that r of phi is just a constant, and then we have circular motion. That's one. So we got circular motion without actually doing much here. And it means that the c, which is now defined in terms of the orbital moment, the angular momentum, and the mass, and the constants in front of the force, that simply tells us that in this specific case, we actually end up with an expression which gives us a circular motion. And you can also see that from phi, the derivative, the angular velocity, d phi dt, because that is now given by L divided by nu over the radius. And this is L divided by nu over a constant square, this constant c. So that means that the angular velocity is also constant. Radius is constant, angular velocity is constant, circular motion. Now comes the next one. So let's now look at the expression here by r of phi equal to c of epsilon, now epsilon of cosine phi. And now we're going to say that epsilon is larger than 0. It cannot be negative because the mass is not negative, the radius is not negative, the radius squared, and the angular momentum is not negative. So that means that the epsilon has to be equal to 0 or larger than 0. But let's now suppose that epsilon is larger than 0, but we make a further constraint that epsilon is less than 1. So if you now take the derivative, d of r, we want to find the minimum here, or the maximum. So we are going to use that to find the maximum and minimum value, which angles, which phi give r max and r min. So I'm going to let you guys do a small calculation now. So if we take some 2-3 minutes and just take that derivative and then find the minimum and the maximum radius by just requiring that that quantity has to be 0. And that will clearly give us either the minimum or the maximum. So just take the derivative of the expression for the radius with respect to the angle phi. And then you ask what is the minimum value and which angles give you a minimum radius and which angles give you a maximum radius. So you need the expression for the derivative. So any good solution for which angles you're going to get here for minimum and maximum? Any suggestions for the values you should get? Maybe it's too late in the afternoon now. Say it again.
At 0 or 0.
Zero? Perfect. 0 and pi are the values which give you the minimum and the maximum. And you can see that if you plug in, if you have a cosine of phi and you put that to 0, that's going to give you plus 1 plus epsilon. If you put it to pi, it's going to give you 1 minus epsilon. And 1 minus epsilon is going to be a smaller value. So that will give you the maximum value. So when you take the derivative, let me now just give you the answer here. So what you're going to get are two angles. So you will find then when you take the derivative that phi equals 0 is one of the answers. And that gives us that r of phi is given by c of 1 plus epsilon. And then the other case, when phi is equal to pi, that gives us r of phi equal to c divided by 1 minus epsilon. And obviously, since epsilon is a positive number, this becomes r min, and this becomes r max. So if we then want to plot things back into the graph of the energy, we are now going to get something like this. So we have this min here, r min, and let's put a prime here. So this is going to be the r max. And then we have the r min here, the r min prime. This case here, that gave us circular motion at the minimum of the potential. Circular motion. Now here, when I look at the energy which we have, so the energy is going to be less than 0 as well. So the orbit is going to be bounded. We are going to oscillate between r min and r max. So this r min, for those of you who are astronomy aficionados, r min is going to define the perihelion, the shortest distance between the Earth and the Sun. And r max is going to define the aphelion, which is the largest distance between the Earth and the Sun. And this type of motion, which you see here, is going to give us elliptical motion. So this is our next step. And, now we're going to show that this actually corresponds to elliptical motion, and it's going to correspond to an energy which is less than 0 on that specific scale we have chosen. So we are going to see now that this is elliptical motion, and I'm not going to be able to finish in time today. So I hope you're not too disappointed, which means that I will sneak in 5-10 minutes on Friday while we are solving the homework. But let's start the kind of mathematics which is needed to show this now. So in order to see this, we are simply going to manipulate the equations. So what comes now is another set of manipulations, which is also relevant for the homework, where you can show how to obtain elliptical orbits or an ellipse. So we just remind ourselves of these definitions. We have that R is equal to C divided by 1 plus this epsilon times cosine phi here. And the only thing I do now is simply to manipulate this equation. So I multiply with epsilon plus cosine phi on both sides. So then I get C. And then we know that R times cosine phi. So if I take this one, we have this definition here, and I have R here and cosine phi. So I can actually rewrite that in terms of X. So what I can do now is simply to rewrite this equation here in terms of R plus, and then I have epsilon times X equal to C, and then I isolate R. So this is C minus epsilon X, and then we square both sides. So then I get R squared, and this is equal to C squared plus epsilon squared times X squared plus 2 times epsilon times X. And then we know that this side here, R squared, is the same as X squared plus Y squared. And then I can rearrange the equation a little bit, and I can isolate this term C squared. So what I can do now, when I isolate C on C squared on the other side, I get 1 minus epsilon squared plus 2 times C times epsilon X plus Y squared, and this is equal to C squared. And now we can do several manipulations here. So what we are going to do now is simply to take this equation here and perform some further manipulations so that we can actually rewrite this in terms of the equation for an ellipse. And then we can go back and see how these different constants are related to R min and R max. So this is basically what we're going to do now, and you will see parts of this in the homework now. But I'm going to do the final calculation here on Friday. So I'm going to leave you guys in a kind of suspension, right? So you're going to crave after seeing the solution on Friday in the first 5 or 10 minutes. I'm almost close to time. And since I took 1 or 2 minutes more last time, I'm going to give back 1 or 2 minutes now, if that's okay. So this equation is the one we will manipulate and obtain elliptical orbits from. Okay. So let's, for those of you who wish to discuss the homeworks, I mean, feel free to hang around. We have time till 5 o'clock roughly here. So feel free to hang around, as always. Yes,